Hello and welcome. Introduction. In this video, I'll show you how to use the analog to digital module or ADC of the TM4C123GH6PM microcontroller to control an LED on the TM4C123G LaunchPad Board. TM4C123G ADC. Now, the TM4C123GH6PM microcontroller has two identical analog to digital converter modules. Now, these two modules are ADC0 and ADC1. The two ADC modules, they share the same 12 analog input channels. Now, each ADC module supports 12-bit conversion resolution. Okay, so here is a block diagram of a typical internal configuration of an ADC module. And I've taken this diagram from page 801 of the TM4C123G datasheet. Now, this is a typical configuration, and it applies to both the ADC0 and ADC1. Now, these little boxes here are the registers, and I'll be referring to some of these registers in my coding or in my program. Now, for example, this block here, SS3, that is the sample sequencer 3. And this is the ADC event multiplexer select, or ADCE MUX. Next is the ADC ACTSS. That is the ADC active sample sequencer. And here we have the ADC SSE MUX3. Now that is the ADC sample sequence input multiplexer select 3. And then we have the ADC SSCTL3. Now this is the ADC sample sequence control 3. And then we have the ADC SSFIFO3. That is the ADC sample sequence result FIFO3. Okay, so the table shown here lists the external signals of the ADC module, and I've taken this table from page 801 to 802 of the TM4C123G datasheet. Now, the signals names are listed here. So we have the AIN0, the AIN1, AIN2, and so on. And it goes up to AIN11. Now, these are analog functions. Now, I'll be using, out of all these signals here, I'll be using the IN0. That is pin 6 of the TM4C123G H6PM microcontroller, or the PE3 pin on the LaunchPad board. Now here is a diagram of the TM4C, or rather here is the pin out diagram of the TM4C123G H6PM microcontroller. And pin 6, which I mentioned earlier, is here, which is PE3, but on the LaunchPad board, here is PE3. The ADC resolution. Now, each ADC module can convert analog values between 0 to 3.3 volts into discrete values ranging from 0 to 2 to the 12 minus 1. In other words, it's 0 to 4095 decimal. Now, if the analog input to the ADC module is 0, the digital value would be 0. And if the analog input to the ADC module is 3.3 volts, the digital value would be 4095. And the resolution can be described as resolution equals 3.3 volts divided by 4095, which equals to 0.8 millivolts. Sample sequences. The ADC0 and ADC1 module has separate sample sequences, that is SS3, SS2, SS1, and SS0. Now, before I go any further, let's remind ourselves, where are these sample sequences located? Okay, so here is the block diagram of the ADC module. All right, so here are the sample sequences: SS3, SS2, SS1, and SS0. Okay, let's go back. So the sample sequences handles the sampling, control, and data capture. Now, the table here shows the maximum number of samples that each sequencer can capture and its corresponding FIFO depth. Now, the FIFO of FIFO is a register that acts as a hardware buffer. All right, it's in other words, it's some sort of temporary memory, and it operates on the principle that the first data that is written to the FIFO is the first data that is read out. Now, the purpose is to enable smooth data transfer between peripherals. Now, the depth of the FIFO refers to the maximum number of samples that can be stored in the FIFO buffer of each sequencer at a time. So, for example, from the table SS3, which is the one that I'll be using, the FIFO depth is 1. All right, so the depth is of SS3 is 1. That means it can hold only one sample at a time. The hardware setup. So here is the hardware setup, and here is the TM4C123G LaunchPad Board, and I would like to focus on these pins here. All right, so I've expanded it. So, and here is the schematic. So we have an R1 resistor, which is a 220 ohm resistor. Then I have a 1K trimmer potentiometer, and the 220 ohm resistor R1, one end is connected to the 3.3 volts pin, and the other end of the R1 resistor is connected to the 1K trimmer potentiometer, and the middle portion of the middle pin of the potentiometer is connected to PE3, and the ground of the board is connected to the other end of the 1K trimmer potentiometer. And so this is the schematic setup, and this is the trimmer potentiometer that I'll be using. The program complete listing. So here is the complete listing of the program. I will go into the details of the program in a few moments. So very quickly, this is the initialization section. This is the definition of the addresses of the registers here. And then this is the beginning of the main program or main prog routine. And it stretches all the way down to this part here. And then this is the, let me just scroll back to the main program for a while. So here are 4 subroutines that the main program invoke. All right, so the first one is the enable clocks proc subroutine, which is here. The next one is the initialize port E proc subroutine. Then the initialize port F proc subroutine, and the initialize ADC0 proc subroutine. And the END here marks the end of the entire program. The program explanation. Now this is the initialization section, and here is the area directive, and my code is the name of the program memory. It can be any other name. It doesn't have to be my code. Then followed by code and read only. These are attributes of area. I'll explain all this in my earlier videos. If you're new to this channel, please refer to my earlier videos. I'll provide the links in the description. And here is the export directive that says the main __ main symbol is made available to other modules and linker. An entry is another directive that basically marks the entry point of the program. And then it follows by a series of definition of addresses of registers. And here is the __ main proc routine, or the main program or the main routine. And here is a series of BL instructions. Now BL stands for branch with link, and basically it's a branch to subroutine. That's how I look at it. So this is a BL to enable clocks, And then here is a BL initialize port E, BL initialize port F, and BL initialize ADC0. Basically, you can view them as branch to enable clocks, branch to subroutine initialize port E, branch to subroutine initialize port F, branch to initialize ADC0 subroutine, and so on. Now, before I go any further, let's take a look at some of these registers, ADC0 underscore PSS1, and then ADC0 underscore RIS, and so on. So, this is the processor sample sequence initiate register. Now, this register is used to initiate sampling in the sample sequences. Now, bit 0 to bit 3, that is SS0, SS1, SS2, SS3, these bits are used to control the initialization of the ADC sample sequences. I've shown this in the block diagram earlier. Now, these bits are write only, WO. They are used by the software to initiate the ADC sample conversion, but cannot be read back. All right, so these are write only. Okay, so here we're back in the code section. So start conversion is a label. Now LDR0, comma equals ADC0 underscore PSSI. Basically, this instruction here loads the address, this address into R0. Now, and then LDR1, comma equals 0x08, that is 08 hexa. Now, 08 hexa corresponds to bit 3, which is the signal, start signal for SS3. That is the sample sequencer 3. And then STR, R1, comma, square bracket, R0, square bracket. Basically, this will store the 08 hex value into memory location pointed to by R0. And R0 is pointing to this address. And basically, this instruction will start the conversion process. Now, this is the ADC raw interrupt status register. Now, this register shows the status of the raw interrupt signal of each sample sequencer. Now, these bits here, bit 0, bit 1, bit 2, and bit 3, these bits represent the raw interrupt in status for each of the 4 ADC sample sequences, which are SS0, SS1, SS2, SS3. Now, each bit here indicates whether a conversion for the corresponding sequencer has complete. A 1 in a bit here indicates a conversion is complete. Right, so here is the weight conversion label, and here LDR0, comma equals ADC0 underscore RIS. Now, this has the ADC0 underscore RIS has an address assigned to it earlier, and then this LDR R1 comma square bracket R0 square bracket basically reads the current value of the RIS register into register R1, and ANDS here performs a bitwise AND operation between R1, register R1, and the immediate value 08 hexa. Now 08 hexa basically in binary that is 00001000, and this bit here corresponds to bit 3 of the sample sequencer 3, SS3. Now if this bit is set, it indicates that the SS3 conversion is complete. And then we come to this BEQ instruction. BEQ is basically branch if equals. Basically this BEQ checks the 0 flag. So here we have BEQ wait conversion. Basically this will branch back to wait conversion if the 0 flag is set. Okay, so this is the ADC sample sequence result, FIFO or ADC SSFIFO N register, where N is an integer. Now this register contains the conversion results for the samples collected with the sample sequencer. Now this bits here 0 to 11 contains the conversion result data. All right, so let's look at these two instructions here. So LDR R0 comma equals ADC 0 underscore SSFIFO3. Basically this loads or copies the address location, which is this one here, which has been assigned earlier. Copy this address into register R0, and the next LDR instruction here loads or copies the latest ADC conversion result, that is bit 0 to bit 11 as seen earlier, from register R0 into R2, so that it can be processed. Okay, the CMP2 comma hash 2048 basically is a compare instruction looking for the decimal value 2048. Now you may ask, why 2048? Basically is an arbitrary figure that I picked up, and because also 2048 decimal is 50% of the reference voltage. And remember, ADC has a 12-bit resolution. Now the next instruction, BGE. BGE stands for branch if greater than or equal. Now, so this branch instruction here says that if the ADC value is greater than or equal to 2048, then the program will jump to the LED on routine, which is this part here, and this will turn on the LED. And B, start conversion, basically this will branch, unconditional branch, back to the starting point where the conversions begins. All right, then if it's not equal, if the result of the comparison is not equal, then it will carry on with this routine, the LED off routine, and the LED off routine basically turns off the LED. and after that it branches back to the start conversion label to restart the ADC conversion process. And the ENDP directive here marks the end of the subroutine. And this is the enable clocks proc subroutine. And the purpose of this subroutine is to enable the clocks for the GPIO-E and GPIO-F and the ADC0. All right. So I've explained the details of this subroutine in my previous video. And if you are new to this channel, you would like to, and if you would like to know more, please refer to my previous videos. I provided the links to those videos in the description. And so these instructions here will enable the clock for the GPIO port E and GPIO port F. And these instructions here will enable the clock for the ADC0 module. And here BXLR will return the control back to the main prog, and ENDP marks the end of this subroutine. Now this is the initialize port E prog subroutine. Again, I've covered this in my previous videos, but I'll briefly go over it. So these instructions here will enable the alternate function for PE3. Remember, PE3 can function as a GPIO and other functions. So now we're using the PE or port E bit 3 as the analog for its analog signal. So we need to enable the alternate function. Then this will disable the digital function of port E bit 3, and these instructions here will enable the analog function for port E bit 3, and BXLR will return the control back to the main program, and ENDP marks the end of this subroutine. And this is the initialize port F prog subroutine. That is the reason why we need to initialize port F is that we're using port F bit 3 because port F bit 3 is connected to an LED on the Tiva C series LaunchPad board. So we're using that particular LED which is connected to port F. So we need to initialize that port. So these instructions here will set port F bit 3 as output. Then this will enable port F bit 3 as a digital pin. And here's the familiar BXLR, returns that back, returns the control back to the main program. And this ENDP marks the end of this particular subroutine. Here is the initialize ADC0 proc subroutine. I will go into the details of the registers involved in this subroutines. Now, starting with the ADC active sample sequencer, or the ADC ACTSS register. Now, this register controls the activation of the sample sequencers. Now, each sample sequencer can be enabled or disabled independently with bits 0 to bit 3. Now, each of this bit, if you put a 0, it will disable the relevant sequencer. And if you put a 1 here, it will enable the sequencer. Let's take a look at the code here. And the first instruction here is LDR R0, comma, equals ADC0 underscore ACTSS. Now this is given or assigned an address earlier, and that address is this. So this address gets copied or loaded into register R0. Okay, so the next LDR instruction here basically copies or load this hex value 08 into register R1. But this 08 hexar is actually in binary 0000 1000. All right, and the NOT of this value is this 11110111. So this is the NOT of this, and the BIC instruction, which is a bit clear instruction. This BIC performs a bitwise AND operation between the contents of R1, which is this one, and the NOT of the contents. Basically, we're having this situation where this value in R1 is being ANDed with this value, and the resultant is all zeros, and this is stored in register R1 when BIC is executed. Now the next instruction, the store instruction, will store the current value of R1, which is this one here, which is this value, into the address pointed to by R0. Though this effectively clears or disables SS3. The ADC event multiplexer select register, or the ADC EMUX, basically initiates sampling for each sample sequencer. Now, each sample sequencer can be configured with a unique trigger source. Now, bits 12 to 15 triggers the source for sample sequencer 3. All right, let's take a look at the code that does that. So we have an LDR instruction here, and so it's LDR R0 equals ADC0 underscore EMUX. Now, EMUX has been assigned this address. So this address gets copied into register R0. Now, the next instruction, LDR R1, comma, equals hex F000, now gets copied into register R1. Now, F000 hexar, that is in binary 1111 0000 0000 0000. So that is the binary equivalent of this hex value. Now, before I go any further, let me just highlight something. Now, the NOT, N-O-T, NOT of this value would be this. All right, basically we invert the ones into 0 and the zeros to ones. So that is the NOT. This is the NOT of F000 hexar. Now, when we come to this BIC, bit clear instruction, basically BIC performs a bitwise AND, A-N-D, AND operation between the contents of R1, which is this one here, with the bitwise NOT of the immediate value, which is this one here. So if we do a bitwise AND operation between these two, which are highlighted here, the result would be this. All right. So basically this clears bit 12 to bit 15. All right. So then we come to this store instruction. This instruction will store the current value in R1, which is basically this, into the memory location pointed to by R0. R0 is pointed to this instruction, and this effectively clears bit 12 to bit 15 of the ADC0_EMUX register. Now the next register is the ADC sample sequence input multiplexer select 3 register, or the ADC SSMUX3. Right, so this register defines the analog input configuration for the sample executed with sample sequencer 3. And this register is 4 bits wide. This 4 bits here, bit 0 to bit 3. Now let's see how this is being used. So we have an LDR R0, comma, equals ADC 0_SSMUX3. That has been assigned this address, so that this gets copied into register R0. And then we copied the immediate value R0 into register R1. And then here the store instruction will copy or store the current value of R1, which is this one here, into an address pointed to by R0, which is this address. That basically effectively selects AINO0. Okay, so this is the ADC sample sequence control 3. That is the ADC SSCTL3 register. Now this register contains the configuration information for a sample executed with the sample sequencer 3. Now this is a 4 bits wide register. Now let's take a look at the code that is using this register. So we have an LDR register R0 equals ADC0 S_SSCTL3. Now this has been assigned this address, so this address gets copied into register R0, and then the next load LDR instruction basically copies 06, which is 0110, that is in binary, that gets copied into register R1. Now the binary of 06 hexa would be 0110, as mentioned earlier. Now that value configures the sample sequencer 3 or SS3 for a single sample with the settings specified in 06 hexa. So it configures SS3 for a single sample. Okay, so we've come to the last 3 instructions here of the program. I basically cover this LDR R0 comma equals ADC 0_ACTSS. I've covered this in the earlier part, and now the next instruction here basically copies this value or load this value 08 hexar into register R1, and then the store instruction basically will store the current value, which is this one, 08 hexar, will store that value into register R0, into the address pointed to by R0, which is this address, and that basically enables the SS3. And then finally we come to the BXLR, basically that returns the control back to the main program, and ENDP here signals or marks the end of the proc or subroutine, and END directive here marks the end of the entire program. Demonstration. Now for the demonstration, this is my setup. I have the Tiva C series LaunchPad board and a mini breadboard, some male to female jumpers, a 1K ohm trimmer potentiometer, and a 220 ohm resistor. Now I have one end of the 220 ohm resistor connected to one of the terminal pins or the of the 1K trimmer potentiometer, and the other end of the 220 ohm resistor I connected to the 3.3 volts pin of the LaunchPad board. Now the PE3 pin on the LaunchPad board I connected to the middle pin of the 1K ohm trimmer potentiometer, and I also connected the other pin, the third pin of the 1K trimmer potentiometer. I connect that to the ground pin of the LaunchPad board. And I have also connected the middle pin of the potentiometer and the ground pin of the potentiometer to two header pins, because I'll be using these pins to measure the AIN0 signal. And finally, not forgetting the USB 2 to micro USB, which you need to connect this to your laptop or desktop. Okay, so I've started the Kyle Microvision IDE, and I put up the code up here. So let me briefly go through it. So this is the initialization part. This is the definition of the addresses used. So this is the main routine on the main program, and it all goes down. This is the LED off routine, LED on routine, and this marks the end of the main program. And then this is the start of the definition of the subroutine. This is the enable clocks prop subroutine. This is the initialize port eproc subroutine. This is the initialize port fproc subroutine. And finally, the initialize ADC0 proc subroutine. And this is the end of the main program. So let me just scroll back up. Right, now let me clear this window. So if I go to project, build target, I got 0 errors, 0 warnings. Now I'll show you my hardware. Here it is. All right. And let me just download the code. And it says program, verify OK, flash load finished. Okay, so the code is downloaded. I have pressed reset and the red LED is on. Now, if I were now to turn the trimmer potential towards the ground, which is this direction, the ground is here. So if I turn, the LED should go off. All right, it does. Now, what I'm going to do now is I'm going to turn the trimmer potential the other way, that is towards the 3.3 volts. Now, the 3.3 volts is the reference voltage. Now, I'm going to turn it to a point where the LED just comes on. And then, after that, I'm going to measure the output voltage set out here. All right, so let me now just turn the trimmer towards the 3.3 volts. LED just about turned on. Now what I'm going to do now is I'm going to use the my multimeter. Let me just bring my multimeter up. All right, and I need to set the multimeter, set it to the correct range. All right, now what I'm going to do is bring the probe up, and then let's see. So I'm getting 1.66 volts, which is approximately 50% of the 3.3 volts. Okay, before we end this video, let's review this section of the program, and I like to focus on this code fragment. All right, so let me bring up the code fragment. Yeah, now the value 2048 or 2448 represents half or 50% of the ADC's range for a 12-bit resolution ADC. Now, basically, this means it corresponds to 0.5 multiply Vref, where Vref is the reference voltage. Now, Vref in our case is 3.3 volts. Now, therefore, 0.5 multiplied by 3.3 volts gives us 1.65 volts. Now, from the demonstration, we see that we measured 1.66 volts, which is close to 1.65 volts. Now, we can get close to, or we can get to 1.65 if we fine-tune the trimmer potentiometer. Okay, so that's it for this video. I hope you have found the contents useful, and I'll see you in the next video. Bye!